You might have heard of these. A hovercraft, which sort of got, I think, taken over by Quadrotors as being the sort of canonical similar hovercraft. I mean, in some of the RL situations, you get lunar lander, which is pretty similar to the hovercraft models. And planar vertical takeoff and landing are pretty similar to the Quadrotor models. Segways, ball bots, these are all kind of in the space of the systems that have often had a lot of interesting thought applied to them from the nonlinear robotics sort of view of the world. I want to introduce them carefully. These are coming kind of in a clump, but there's a method to the madness. So we've done very simple systems so far, just double integrators and pendulums and the like. And we've introduced a few algorithms. And now the cycle in the class, I'm going to try to introduce more interesting systems, more closer and closer to, let's say, Atlas doing a backflip. And we'll try our best to use all the algorithms we already have. And we'll introduce new algorithms only when we need to sort of solve the new problem that's been put in front of us. So when we introduce a system or a version of problem for that system that breaks our other algorithms, then we'll bring in a new algorithm. So that's kind of how it's organized. OK, so I'll start with the Acrobat and Cartpole, and we'll show its general for a lot of these systems, some of the basic results we're going to talk about today. So Acrobat is basically our double pendulum, OK? Two-link pendulum. It's got inertia typically, so it's not just a simple pendulum. It's an inertial pendulum, OK? And it's got an actuator applying torque at the elbow, but I didn't have enough funding to put an actuator at the shoulder, OK? So its configuration space is simple, theta 1, theta 2. Its action space is just the torque at the elbow, if you will. And to make it interesting, we want to make that a bounded torque. OK? And it's sort of meant to be it's called an Acrobat because it's meant to be a little bit like an acrobat on a high bar, right? Where someone who might want to flip up and balance upwards, with their hands down and their feet up on a high bar, they might be in a situation where they don't have a substantial amount of torque at their wrists, but they have a lot of body torque that they can apply at their waist. Okay? And even though we didn't have enough money to put the motor at the shoulder, that robot can still do awesome things like an Acrobat. So this is one that we built in lab a few years ago. Ooh. It's supposed to be full frame rate when you're on the projector, but wow. Why is that so bad? OK, well, hopefully you can sort of fill in the details. Sorry for the choppy playback there and the weird audio. OK, but this is actually a fairly massive Acrobat. Big aluminum joints with carbon fiber rods. It's got a motor. You can see a motor down here if you're looking carefully, but it's actually driving only the torque at the elbow through a shaft that's plumbing through here. The reason for that, as we'll come to understand as we understand the dynamics of the Acrobat better, is that you want the mass of this link. You want the inertia of this link to be large. So what you really want is that there's a lead slug at the end of that, okay? That you don't want to get in the plane of the Acrobat, for instance, okay? That's a big hammer on the end. And we can, you should be able to play with this system. So I have a notebook here where you can interact with everything. So just open up my MeshCAD here. If it helps your intuition, the first one here is just the passive dynamics of the Acrobat, but I put in a little slider, and you can try your hand at trying to swing up the Acrobat with torque. I suspect you won't be successful. It's not because I made it, you know, it's a little bit laggy, but even with that, it's actually really, really hard to do it right. Okay, but that's the basic dynamics of the Acrobat available for you. Now, despite having missing a motor, you saw it sort of slowly swing up and get up in the video, but actually you can do pretty awesome swing ups too. So this is sort of the optimized, trajectory optimized swing up of the Acrobat under some torque limits, and we'll have that solution available in another notebook soon. Okay. So it's also, if you note, stable at the top. The real robot stayed up at the top, and that's pretty cool that it can stabilize that two-link system even though there's no motor there. You would think that it would try to fall down and that this motor wouldn't have enough ability to stabilize that, but actually it does, and we'll see that in details today. Okay, the companion system for that is a Cartpole system. Again, these are both available in like a lot of the RL gyms, RL benchmarks as the classic control problems. Okay, this one is the simple pendulum with just a mass over here and a mass on the cart. Okay, and the control action is just to apply a force on the cart, and there's no actuator at the pin joint here. This is theta, but there's no actuator there. So it's kind of like a simple pendulum attached to a double integrator mass on wheels. Okay. And similarly, this one, even though it's missing an actuator, you can do awesome things about swinging up and balancing this guy. Forget about the detail of this approach here, but just to see what the system is capable of. I think the network is not doing its thing, maybe, but don't worry about it. Don't try to change it, but you're not connected either? Maybe if I pull this out, it'll be better. I have this one local. Let me just play it here. Even that is playing badly. What the heck? I ordered a new laptop, and this one I think knows that I ordered a new one. Because it was kind of fine, and it just started dying while the other one's shipping. It ran out of hard drive space last night. Okay, but hopefully you get the basic idea there. Okay, so this one, Q, is now the X position of the cart and the angle of the pole. U is the force on the cart. I'm going to say that U is again limited to make it interesting. And this one also often in practice has some other constraints, like it's on a track or something, and you don't have an infinite run on the cart. So you actually have some constraints that look more like this, too, some state constraints. Otherwise, you run into the wall. OK, so the equations of motion for both of these are the standard manipulator equation form, right? So Q I've written up there, U I've written up there. For the Acrobat, B, which is applying only an actuation to the second acceleration. So U is a scalar, and Q is 2 dimensions. So B is going to have to be a 2x1 matrix. And it's really as simple as being the 0, 1 matrix here. If you had a transmission or something, you might put that in here as something other than 1. If you had a gearbox or something that was amplifying your actuator. But for our purposes, this is just 0, 1. And for the Cartpole, B, the control input, it's the same size here. It's also 1 to 2. So this has got to be a 2x1 matrix. And this time, it's applying, it's generating acceleration directly on the first coordinate. So it looks like this. No surprise, they're both underactuated, right? And the interesting task for both of them is to take your system from an arbitrary initial condition, but typically something, kind of dangling near the bottom, and figure out some feedback control law in general to try to swing up and balance at the top. That's the task. Okay. We can write that in the various different cost functions using the language of optimal control. In fact, the cost function we used for LQR would be already enough to be interesting for this. If we said that our instantaneous cost was just some quadratic cost, which said that I want to be close to the upright. So I'll write my same quadratic form, but this time I'm going to say I'm going to take it the difference between my current state and the upright state, and I'll use that as my quadratic form. And then for my actuator cost, I'm happy again to do something like this. Okay, that's a perfectly reasonable way to write a cost function, saying, I'm at 0 cost up here if I'm applying I'm at the top and I'm applying 0 torque. And if I'm a little bit the farther I am away quadratically, I'll penalize myself in state, right? And similarly, I want small actions, so I'll make R positive. Okay, so how do we solve this? We've had a few different approaches that we've talked about. We've talked a lot about dynamic programming and the numerical implementation that was the value iteration algorithm. So a natural first question would be, does value iteration, as we've talked about so far, when I put in these equations of motion and this cost function, will it give me a swing up and balance controller? Okay, and I think the answer is the default. The answer is yes if you were to put enough behind it. Yeah, I would say the answer is yes, but. All right? So if you discretized your space finely enough, right, then yes, it will eventually work. But what is surprising, if you go to try it, with the naive value iteration algorithm that we've talked about so far, it takes a ridiculous amount of discretization to get even to stabilize around the top, right? Because the Acrobat in particular is actually pretty hard to control. The control law, if you get it a little bit wrong, you're falling down, okay? it takes a ridiculous amount of discretization at the top to get an approach that would practically stabilize the Acrobat. Okay? We'll see the continuous time value iteration is going to go farther in this, and that's what we'll talk a lot about on Thursday. But the default out-of-the-box value iteration, I would say this is at the boundary of the type of system you can do in practice, and it's not fun. It's like, it doesn't feel like the right solution to the problem. I mean, the other algorithm we've talked about is the limiting cases of dynamic programming where we had closed form solutions. The most important, the one we spent the most time with was LQR. LQR was for linear dynamics, right? But I showed you a video of it balancing Atlas. So the question is, how far can I get with something like LQR on these systems? And the answer, maybe you won't be surprised, but we'll see in some detail here, is that for the balancing portion, once I'm sort of close to the right solution, actually LQR is going to be an excellent solution. It's going to be a local approximation of the true solution of this problem. And it's going to be good in the balancing regime. But it's going to be insufficient to do the swing up problem. But because we can understand so much about these systems and this dimensionality, I think seeing how well LQR does and understanding its limits is going to be very useful. So I want to spend a little time now thinking carefully about what happens when you apply LQR to a nonlinear system. So I have this form. I know how to control or design controllers with LQR in this form. Okay, how do I start with this and get to something like that? I mean, you can linearize a nonlinear equation. What does that look like in the dynamical systems sense here? You're going to pick some linearization point. That means a nominal state and control pair. For us, we're going to pick the state when we're at the top and the u that is 0, because that would be the equilibrium and the zero cost configuration. And then I can take a Taylor expansion of this, a first order Taylor expansion, and write that x dot is approximately this at that sample point plus the partial derivative of it evaluated at the sample point. Right, that's just a first order Taylor expansion of any nonlinear equation I could have done that for. I chose to write that this is approximately equal to this. Sometimes people write this equals this plus higher order terms. Same thing. Okay, but let's just write this instead as x dot 0, which would be my, that's my derivative at the configuration, at the nominal configuration. And let me call this partial derivative a matrix A. Call this one a matrix B. And now if I pull this to the other side, what I can see is I can write this. Which suggests that the answer is, if I want to make a linear approximation of this, I have to change coordinates. So I'm going to use the notation x bar is x minus x0. So this is the state, but in the coordinates relative to whatever my point I'm linearizing around. U bar is similarly u minus u0. And if I were to take the derivative of this new coordinate, I also have that x bar dot is just x dot minus x dot 0. Okay? And in that coordinate system, then I have x bar dot equals ax bar plus b u bar. Okay, so that's how the mechanics of it work. I do have a linear approximation in a new coordinate system potentially around my nominal point. Now, what does it mean to have my nominal point dot, the derivative of that nominal point? It's a little weird. If this is non-zero, then it's like I have a moving coordinate system. My coordinate system is moving over time. For today, we'll be happy to take that to be equal to 0, so we'll just have a fixed coordinate system. But we're going to generalize it and use this fact later when we want to linearize along trajectories or things like that. Okay, so but for today, x dot will be 0. I've just chosen x dot, or x0 to be the upright that's fixed over time. Its time derivative is 0. Okay, when I was a young faculty, I used to say, linear control, everybody talks about linear control, but you really have to think about the nonlinear dynamics of your robot, right? And that, linear optimal control doesn't think about nonlinear dynamics. I mean, that's true. But there were a few projects along the way that made me realize how good linear control is, and how much of the nonlinear dynamics it can actually reason about. And I want to just sort of give you a little bit of a taste of that right now, okay? So let's just think about what this looks like for the pendulum, okay? So we had ml squared theta double dot plus b theta dot mgl sine theta equals u, right? And this generated this eyeball thing, right, in state space. Right, this was the phase portrait of the nonlinear equations. And now I want to linearize those equations around some point. Okay, I'm going to pick the upward configuration of the pendulum. So I'll linearize around that point, okay? So if I were to write this as x dot, I'll write it out just to be careful here, theta dot, and then x dot is theta dot 1 over ml squared u minus b theta dot minus mgl sine theta. So this first line is already linear, so my linearization, I hope, will get the same thing back. This one's actually, pretty close, but they've got that sine theta that has to get linearized. Okay? So when I choose x nominal to be pi 0, u nominal to be 0, and I take my partial derivatives of that function, I'll get my A matrix just by taking the partial of this with respect to q is 0, with respect to q dot is 1. This term with respect to q is the negative g over L cos theta. And then this one's negative b over ml squared. Okay? But it's all just, it's just the same standard mechanics. Okay? When I evaluate this now at x equals x0, u equals u0, that means I get to evaluate this at cosine of pi. I get just 0, 1, positive G over L okay, so that's my A matrix, if you will. The B matrix similarly is just 1 over ml squared. Now, I'm going to go ahead and set M and L. I'm going to basically set all the coefficients to 1 because that's going to make me write less things on the board. Okay, so let's set mass equal to 1. Set the damping equal to 1. So actually, I'll set the damping equal to 0. Make that even easier. Length equal to 1. Gravity, I can't quite get myself to make it 1. I'll make that one 10. Okay. That means that my linearization here, with that substituted in, gives me some pretty simple matrices to think about. Okay, so two-dimensional linear systems, you can do the same graphical analysis we did before, but you can use the eigenvalues and eigenvectors of A to understand the two-dimensional plot. Okay, so if I were to try to plot what's the dynamics of this with u equals 0 for a minute, that means that's going to be x bar dot equals a of x bar. I can plot that. I can plot that by understanding the eigenvectors and eigenvalues of A. Okay, so you can take the eigenvectors of A, right? So I'll take the determinant of A minus lambda I, set it equal to 0 to get my eigenvectors and eigenvalues of A. These are my characteristic equation. Just dusting off things. I just wanted to convince you that these are things you know. Okay. That turns out to be lambda squared minus 10 equals 0. Lambda equals plus or minus square root of 10. Okay. And the corresponding eigenvectors are 1 square root of 10 and negative 1 square root of 10. So let me plot those eigenvectors and eigenvalues here. I have two lines. I have 1 square root of 10, which looks like this, say. I've got another one that's negative 1 square root of 10, looks like this. The eigenvector corresponding with this is the lambda 1 square root of 10. The eigenvector corresponding to this one is lambda 2 is negative square root of 10. Okay. Why is that associated to the phase portrait of the system? Why does that tell me what I want to know about the phase portrait of the system? It's because I can write any, this is the modal analysis, right? So if I have x dot equals ax like this, I know that I can write any x as long as these things they span the space. This is just two vectors that span the space. So I can write any x as a linear combination of v1 and v2. That's just saying those are linearly independent, so I'm able to just write any value here as the linear combination of those. And I'm going to use the fact that those are eigenvectors to say that the time derivative here is just alpha 1 lambda 1 v1, alpha 2 lambda 2 v2. So my phase portrait, remember, was done by drawing vectors that were the value of x dot. That's a two-dimensional vector, right? And it turns out that those vectors are trivial to draw on the eigenvalues, on the eigenvectors. And they're linear combinations of these everywhere else. That means for this linear system, I can go through and draw the whole phase portrait. And you did this in 1803 or whatever equivalent, right? I can go through and fill in the phase portrait for this system as linear combinations of those eigenvectors and eigenvalues. That's just my graphical analysis of the system A equals 0, 1, 10, 0. But what I want you to see, this is, if I overlay the eyeball for the nonlinear system, right? It's really good, right? This is, remember over here, this is linearizing around this point here, not the origin. We linearized around a different point here. And the phase portrait had a particular characteristic around there, okay? And the difference between the linear system approximation and the nonlinear system, it's real. Of course, there is a difference. But, there's a big part of state space where it's pretty darn good. Right? You have to get way out over here. I mean, this is not drawn perfectly to scale or anything like this, but but in practice, the linearization is actually surprisingly good. I'd say far away from the linearization point. At some point, it's ridiculous, right? Because over on the other side of the eyeball, this vector's pointing up, and the linearization is still going to be saying down, and it's just as wrong as you could be, right? You can get too far from it for sure, but there's a big area of state space where it's pretty darn good. And for me, it was like seeing some pretty complicated UAV maneuvers where we got hit by a gust of wind, and the linear controller just took a highly non-trivial path to stabilize the controller. I think that was the experiment where I was like, you know what, actually linear control is pretty darn good. I should stop saying that linear control is bad. Does that make sense? Okay, so you can imagine now that if I were to take my linear optimal control toolbox and apply it to the linear system, I'll get if I called LQR, for instance, I'd get a linear feedback controller and a quadratic cost to go, which guess what is going to be elongated in this direction, which is exactly like we saw before, where the direction where you're riding in your momentum here, you're going to have an elongated, your cost to go level sets are going to be stretched out in those axes and sharper in this axis. And you'll get a cost to go function that is, understands somehow the dynamics of that system, at least locally. So we're going to see that this recipe is going to work for Acrobots, Cartpoles, Quadrotors, right? We'll run some examples, Ballbots. Okay. But I want to take a minute to appreciate it, that it's solving a pretty non-trivial problem. Even the control design part of it. We've got this nice, simple representation of the dynamics there. Once I get a two-dimensional dynamical, two-dimensional linear dynamical system, I can show a lot of cool things fast, right? So let's appreciate, I'll even write it, let's appreciate LQR for a second. Okay, so if I just am solving LQR for this system, which now I hope you have, because it's connected to the pendulum, you sort of have some physical intuition about it. When I choose Q here, you'll see in the code, in my notes or whatever, I almost always do it like that. And then I'm happy to take R equal to 1. Anybody know why I always do 10 and 1? Why would I do 10? It's pretty weird, pretty arbitrary. If you've tuned PD controllers, you might have used a 10 or something before too, right? Yeah, do you know? Say it a little louder. Yes, yes, exactly, right? So it's my dimensional analysis. He said the derivative term is like a tenth of the original term, right? So I guess to make the dimensional analysis story here, what I'd like is that if I multiply theta times Q11 times theta again, right? So if I just take this element multiplied through, I want that to be approximately the same as theta dot times Q22 theta dot, right? Those are just scalars, but. Right, and this is in units of radians per second, and this is in units of radians. Since I tend to build robots that are like on the order of a meter long, if I was like working on micro robots, I would probably use a different number there. But all of our robots are on the order of a meter. Okay, so my dimensional analysis tells me my time constant is square root L over G here, square root of 1/10. If I stick in square root of 1/10 twice, I get 1/10, and it tells me I should be 10 times bigger just to make those units approximately the same, right? If you're working with robots that are in Earth's gravity and are about a meter long, that's a pretty good rule of thumb. Make your costs on your positions about 10 times bigger than your derivatives, right? Okay, so if I were to just run LQR a bunch of times, you know what, I'm actually going to, let me make this a constant. Instead of just 1, I'll take this as a constant. And I'm going to run LQR a bunch of times as I change the value of R here. And I want to plot K, the values of K. Right, K is, there's one input, there's 2 state variables. If I have U equals negative Kx, what size is K? It's going to be 1 by 2, right? It's got 2 values there. So if I pick some nominal value, let's say 1 for R, I get a couple, I'm going to use blue and red for K1 and K2. I get a particular value of K1, particular value of K2. And what I want to think about here is what happens as I change R and make it bigger and bigger and bigger, increasing towards infinity. What do you think is going to happen? What is your intuition about R? R says I want to penalize actions, right? If I pick R bigger, then I should use less U. So that would tend to make K smaller. So these things are going to, as I increase them, they're going to go down. That's for sure true. But what I want to think about is what's happening as R gets really big. Are they going to go to 0? It'd be a totally reasonable thing. What do you think? Yes?
They'll go to the smallest possible thing that gets you there?
Good. He says that we'll go to the smallest possible thing that gets you there. Right? There's some constraint. They can't go all the way to 0 because then the system's going to fall down. And then the state cost would go up. Okay? So actually what happens is these things asymptote. This one asymptote, I happen to know they asymptote at 20, and this one asymptotes at like 2 square root of 10, I think it was. Okay? Which these numbers being related to that 10, or that 10 actually, are not a surprise. Okay? But LQR is doing something pretty clever, right? It's parameterizing a class of controllers with Q and R, but that class of controllers is constrained to be stabilizing controllers, right? In fact, if you were to, the class of stabilizing Ks actually is non-trivial. I can make that point quickly. If you ever tuned up a PD controller, okay, and you made K1 bigger and then K2 bigger and then something went bad and something went good, it's non-trivial actually to find the balance between K1 and K2 and to get good performance. Okay. As a very simple example, let me parameterize it like this. So I can find, I'm not going to even tell you what the A and B are, but there's a whole class of A and B matrices such that if I were to put the controller in feedback, I'd get that as my closed loop. Right? This is just the A minus BK matrix. You know where that's coming from, right? I've got x dot equals ax plus bu. I apply u equals negative kx, then the closed loop dynamics is a minus bk times x. So this is just an example of a closed loop system that could be parameterized by 2 feedback gains k. And if you were to plot the eigenvectors and eigenvalues, if you were to plot by an analysis again of, let me plot over K1 and K2, the set of Ks that makes this thing stable or not stable, it turns out that the threshold is that this is K1, K2 equals positive 1. This is K1, K2 equals negative 1. Some of you have done this in linear control and recognize those kind of terms that pop out. But what my point for illustration right now is that the set of stable Ks is in blue. The set of unstable Ks is in red for this particular system. I can make harder systems, but this one just is enough to point it out. But I could take 2 perfectly good stable Ks, draw a straight line between them, and end up with an unstable K. Searching over the class of Ks is not a convex problem. That's what that's saying, okay? And you could have 2 different controllers that you're perfectly happy with, and the controller that averages them is bad. This is actually a really interesting topic. We're going to come back to it when we talk about policy search. You can imagine if you were an RL agent trying to search in K1 and K2, the fact that this set that you could potentially be stable and then unstable could have implications. It turns out, in this case, this is one of those cool cases where even though the set is not convex, all local minima are global minima. It's one of, you know, we'll have that lecture, but just as a teaser, policy search actually works pretty well in this problem. But you should think about LQR as a better way. Like if I'm, as a human, if I'm just picking K1s and K2s, I can get myself into trouble. Certainly with an Acrobat, you know, finding K1s and K2s that make this thing stable is not an easy task. And what you should think about as LQR is a different parameterization, where instead of mucking around with K1 and K2, I'm going to muck around with Q and with R. Every time I put a Q and R in, I get a stable K out, right? All I have to worry about with Q and R is that they're positive definite. That's a much easier thing to think about. So any positive definite Q and R will give me a stabilizing controller, assuming my model's right and those kind of things. So LQR is doing a pretty awesome thing for you. You can imagine trying to search directly in Q and R as possibly a better thing. People have looked at that. It turns out, I mean, for those that want more gory details, but it turns out that there are stable controllers that you cannot, that are not parameterized by the solution to LQR. So even though, so it's true that every Q and R gives you a stable controller. What's not true is every stable controller you could find a Q and R, right? It could be there are stable controllers that you could not parameterize through LQR. Whether they're important or not, who knows? There are other parameterizations of the stabilizing controllers, which do get the entire family of stabilizing controllers. And so there's layers of understanding here, right? Lots of good things to know. Okay, but LQR is doing something pretty awesome here. Any questions about that? Okay, so let's put it to work on bigger systems, the ones I can't plot phase portraits of or make the dynamics into a 2x2 matrix. That linearization recipe that I gave, that is quite standard, didn't assume much about F, okay? Maybe there's some smoothness assumptions there, but as long as those gradients exist, that's a perfectly reasonable thing to do. If you do it to the manipulator equations, though, you're doing it to something special. The manipulator equations are special, too, right? So linearizing the manipulator equations is easier than somehow linearizing arbitrary F. So I can apply this at scale with even taking only a handful of derivatives. Now, here's the one thing. This is the one board right here. I'm going to do something I hate doing, but I've decided in life that it's okay. There's not a better solution. Okay, there's a B that we always use in the manipulator equations, and there's a B that we always use in linear systems. And I'd be like unhappy for the rest of the semester if I used anything but B here or anything but B here. Okay, but on this one board, there's two B's and they mean different things. So I'm going to put a little m here to remind myself that this is the manipulator B. Okay, and that's the linear system B. I apologize. I couldn't think of something better. Okay. In general, I've got x is just q dot. U, of course, I've already got as a vector here. X dot has all this same beautiful structure where the top is simple. It's just Q dot. The bottom looks scary, honestly, because it's got this M inverse here, and then it's got all my simpler terms on the inside. So if I want to start taking partial f, partial x of that thing, you know, I got to take out my chain rule through the negative, you know, the inverse of a matrix, and these matrices get big, and that inverse matrix gets gross analytically. It turns out, you know, there are basic conserved quantities in these equations, and lots of things cancel out in a beautiful way. And actually, the gradients of this thing is way simpler than if you just applied like autodiff to that equations. You can, and if, you know, in PyTorch or something, you're fine with that. But you don't have to do that. You don't even need a differentiable simulator for this one. This one's pretty easy. Partial f, partial x has all this beautiful structure. This one's just the identity matrix up here. And the chain rule goes through so that I get M inverse just the gradient of my potential energy with respect to Q. B is similarly simple. Okay, so I can linearize big old robots, right, with this. It's not computational. It's you know, this even this, because this is the gradient of a potential function, is simple. You know, the way that we construct tau g in recursive rigid body algorithms and stuff. These gradients are simple. Okay, so you know, this is not a bottleneck. Linearizing even a very big system is not a bottleneck. And when we get a linearization, so we can get like x dot equals ax plus bu of the Cartpole or the Acrobat around the top. The next question is LQR going to work, right? You asked a good question last time about controllability, right? So I can go from that to x dot equals ax plus bu. This is in the error coordinates, but I'm going to just, I'll write it here to be careful here. I won't. I'll just go ahead and show you here. All right, LQR for the Acrobat. If I got my Meshcat open here. So what I'm going to do here, I'm building up I'm going to call LQR in the middle. This I can make bigger, sorry. I'm basically going to make a little controller by saying linear quadratic of the Acrobat. The context in Drake is just the state and input. So this is just giving me my x0 and u0. That's a way to pass that in. I'll say something about that later. Roughly, this is linear quadratic regulator, Acrobat, x and u, q, r. Inside the LQR function, it's going to linearize the Acrobat, okay, and then kick out a controller to do that. And I'm going to put that controller into a feedback combination. I'm going to set the robot in initial conditions near the top and give it a perturbation off the top. And you'll see it respond to some perturbation off the top and use the LQR controller to respond. Okay. Normally it succeeds a few times before it fails, so that was kind of stole my thunder here, but it's getting knocked around. Okay, and as we saw from the previous pictures, you can have, there's a limit to where the linear controller works. I got particularly unlucky that time, I think, but there we go. That's a more reasonable response. Okay, and depending what random perturbation I draw, it works a lot of times, and then sometimes it's just too far away and the linearization fails. And then things get pretty bad pretty fast, by the way. Okay, exact same recipe works for the Cartpole. Here's a little Cartpole. Do exactly the same thing. That's its nominal configuration. I'll knock it around at the initial conditions, and it'll sometimes take a pretty long path to get back and stabilize. Okay, but LQR with just Q is 10 times the angle. Well, this one actually doesn't have the. I guess it does. Yeah, but trivial Q and R gives you good balancing performance on a Cartpole. The cool thing is it works for all kinds of other systems. Okay, so we'll do the planar quadrotor is another one, right? Where I have Q for this is X, Y, and theta. So I'll have the little quadrotor that I draw like this in the plane, okay, that's the XY position, and it's got some nominal angle theta, okay. And then U is the propeller, the thrust you get from a propeller. A very crude first approximation is just to say that you can control the force directly on that propeller. And here we typically say you've got a directional prop, so you can only produce force in one direction. You can't push yourself down. You can only pull yourself that way. Okay, and you can write out the equations, and we've got them in the notes, the full equations for these things. You can stabilize around the nominal condition. This one is interesting because to find a fixed point to stabilize around, this one, or Q0 even, could be 0, 0, 0. I'm happy with that. But U0 can't be 0, 0. If I've got no thrust coming, my quadrotor's falling out of the sky. So I need to apply a force that's like mg over 2 from each of those propellers is basically what you need to do. In order to find an equilibrium point that I'm going to linearize around. Okay? But if I find an equilibrium point that I like for my quadrotor, I can just call LQR plant context QR with a bunch of 10s and 1s. Okay? And this one I actually drew the little curly. I do this on the board, so I figured I'd do this in Matplotlib. I get my cute little animation. Here we go. Woo. Do my random initial conditions. Okay. And this works. I mean, you could put this on a real quadrotor. It's good stuff. You can do better. Those of you that play with quadrotors, in AeroAstro will be doing better, but this gets you pretty far. Okay, and then same thing works in 3D. In the 3D quadrotor, I'm going to use, in this example, X, Y, Z, yaw, pitch, and roll. where the linearization of this is simple and uses the same recipe as before. That parameterization has problems. For those of you that know about quaternions and other things like this, you can do the same work with quaternions, but if you want to use the recipe from today so far, just use a yaw pitch roll representation of 3D orientation. As long as your quadrotor is not upside down, it's going to be okay. And if your quadrotor is upside down, I guess you're already getting out the spare propellers or something. Okay. Oh, by the way, the Skydio guys are MIT alum, right? So I asked them for the CAD file. All right, here you go. So 3D stabilization of a quadrotor just kind of works. Just to show one more, I whipped up a Segway, a 2D balancing ball bot. This one for grins. I tried to do each one of these differently, just so if you want to look at the code and see like, oh, how did you make a robot or something? So one of them I loaded in from a URDF on the file. This one I just wrote a little URDF right in the text so you can see it. The URDF is the robot description format. I just call linear quadratic regulator. Q is 10, 10, 1, 1. I didn't even remember that I did that, but yeah, it's always 10, 10, 1, 1. Okay, and I can have a little ball bot that tries to stabilize itself at the origin. Right? So in the vicinity where the linearization is good, this is a great recipe, right? Changing Q and R can, give you it gives you some control over the preferences of which states are more important, where am I willing to pay control effort, how do I want to trade off control effort with state cost, how fast I converge, for instance. But that's a recipe that just kind of works. There's a subtlety here I'll just mention. It's written in the code, but you might think if I were to simulate this that I write roughly the coordinates of the same parameterization as the quadrotor, but I just happen to apply some force on the ground. That's not what I've done here. I've parameterized the ball bot in the coordinates of the ground. It could never leave the ground, because I don't want to think about what happens when the robot comes into the ground. That's when you get into walking robots and stuff. You got to think about all the impacts and collisions and forces that are on or off. So this is not something I did to cheat. This is what people do when you're making cars or unicycles or bicycle models or whatever, is you typically write the coordinates in the constrained dynamics. And so in the dynamics of that constraint, so you have less state variables, and then your linearization is good. Okay, you can take gradients through full dynamics with equality constraints, but it's more work. This is, to make this recipe work, I only write the variables such that the robot is always on the plane, can't lift off the ground. Questions? Yeah.
How computationally difficult is it to calculate the initial conditions that a given control is stabilized?
Good. So the question is, how computationally difficult is it to calculate the initial conditions? So actually, the fact that these gradients are simple is also what you need, because they can be simple in terms of, so what you want to find actually is that these gradients are equal to 0, okay? So it's actually, if you solve it as a big nonlinear optimization problem, it can be hard, but if you exploit the equations of motion of the manipulator, it's actually pretty easy. For instance, for it to be an equilibrium point, Q dot has to be 0, so this term just drops away, right? Q double dot has to be 0, this term drops away. So really all you need to do is U equals negative tau G, and the gradients of tau G are all you need, basically. So a lot of people make it harder than they need to because they think about it as x dot equals f of x, but for robots it's this. It's pretty simple. Great question. A lot of times that's a small nonlinear optimization to do that. Other questions about that? Yeah. No? Yes.
I'm curious about like, so it seems that M is originally in the first line of the equation, M is a function of Q.
Yes.
I'm wondering when we take derivative of delta L over delta X, like why don't we differentiate through M?
You do. So good. So I thank you for asking that. So he says, why didn't I take a gradient of this through M? Why didn't I have a partial M, partial Q here? Yeah, no. So this is surprising. It looks like I'm missing a bunch of terms. If you go through and take the gradient of this and the gradient of this and all the things with the chain rule, you will get a lot of terms, which if you then apply these governing laws, they cancel out. And it's surprising that the gradient turns out to be as simple as this. This is a function of Q. Naive, you would need to take that. If you were doing autodiff, you would be going through all that, but you would end up with this. That's exactly the point. Thanks for asking that. Okay, I want to make one last point. Going back to the when is this stuff going to work? If I can take my manipulator equations and I get down to this system, we said that the property that makes LQR succeed or fail locally is related to the controllability of the system. And I want to say that more carefully now. Technically, the condition actually is that LQR will work when the system is stabilizable. Okay. But we're going to define stabilizable by defining controllable first, because that's a big part of it. Okay. So controllable so a system, even a nonlinear system, x dot equals f of x u, is controllable if the game is you give me any initial conditions and final conditions. For all, if you pick those initial conditions and final conditions, if I can find an unconstrained u trajectory that gets me from x0 to xf. And it's actually a finite time trajectory. Okay, that's a big pile of ideas there or something. Okay, but roughly, importantly, there's this notion of controllability, which says if I have two different states of the system, there must exist some actuation, u, that could take me from that state to the other state, for any two states. It happens that for linear systems, just asking, can I get from any state to the origin is an equivalent question, because the linear systems are not coordinate. This property would not be coordinate dependent. It doesn't depend on xf. You can just set xf equal to the origin, and that's fine. And it happens that there's a check that's very natural, based on the controllability matrix, to check this condition for linear systems. Okay? In Drake, there's a function that says controllability. You can pass it either the AB matrices. I guess you have to pass it the AB matrices, right? And it'll give you back a controllability. You can either ask it, is it controllable, true, false? Or you can ask it for the controllability matrix. Okay? In fact, in my notebook here, I called those functions and printed out, just before I ran anything, I printed out the controllability matrix, the singular values of the controllability matrix for the Acrobat and the Cartpole. I'm not going to throw a bunch of controllability math in front of you at the end of the hour, but I do want to make a super important point, which is that just because a system is underactuated does not mean it has lost controllability. The Acrobat, the Cartpole, all of the systems we saw today, they are underactuated. They are missing actuators. But they can still get from any initial condition to any final condition. So what I should say more precisely is, all I've proven here is that the linearization is controllable, that they can get from, in the linearization, it can get from any initial condition to the origin. Okay? So being underactuated does not imply uncontrollable, as we've seen. And I think the Acrobat is maybe my favorite example of that, right? Even though I don't have an actuator in the base, which seems like it should be the most important joint, right? Because my gosh, that's the whole thing that's what's keeping everybody up, right? I can still control this joint, or I can control this joint, and over time I can control them both. I can find control inputs that mix the regulation of this and this state variable, even though I only have one control input. Those are not the same ideas. Underactuated means I can't instantaneously control both of them. Controllability says over time can I control both of them. All of the examples I showed you today are controllable, but they are underactuated. If you care, I mean, stabilizable is a slightly weaker form of controllable, because if you have a system that's already stable, it's okay if you can't control the directions that are already stable, right? So if I had a system with no actuators, but it was stable, then that's still stabilizable, I guess. Maybe that's a weird limiting case. Maybe I shouldn't say that. But let's say I had one actuator, like I had a pendulum over there that was controllable, and I had, like, I don't know, a bunch of other things here that were stable, not connected to that, right? Stabilizable says I can get myself to the origin. It could be via control inputs, or it could be just through the passive stability of the system. So you can have systems that are stabilizable even if they're not controllable. That's just a technical thing, okay? That goes on top of it. But this, I think, is a fundamental idea that I want to make sure you really grok, right? Underactuated does not imply uncontrollable. Interestingly, if you had that ball-bot system and you wrote the equations of motion to allow it to fly through the air and drive along the, okay, not only would you have to deal with the fact that there's a ground, also that system is not controllable because you don't have any actuators that would allow you to get to arbitrary places in the air. So if you took the naive equations of motion of the ball-bot, you would say they're uncontrollable. It's only the reduced equations that say I'm always on the ground and I've parameterized my state that way. Those equations are controllable. Okay? That actually happens. I mean, walking robots, the naive linearization of walking robots tends to not be controllable because of static friction, basically. I can't instantaneously move myself. In the linearization, I can't, like, move my foot that way because static friction is resisting that. Okay, I actually have to do something nonlinear to move my foot around. Okay, those things, once you get constraints and on-off dynamics, things get more complicated. But LQR is a pretty darn good tool. It only solves the balancing part of the problem for today. Okay, so when we're in the vicinity where the linearization works well, this is an awesome tool. We'd like to think that if we're solving value iteration, let's say over the whole space, that the solution at the top would look like the LQR solution. It's not even, you know, in the location, in the vicinity of that linearization, it's even a good characteristic of the optimal cost to go. Okay, but we're going to deal with the rest of the swing up problem next time.